Hello, ladies and gentlemen, and it is Tuesday night at about 3:54, and I've been sitting at my desk ever since class has ended. I want to be able to get through to you guys how the fundamental theorem is connected to derivative calculus and integral calculus, and I'm trying to do it in a way that isn't too technical and is within our grasp. And I think I've finally done it. So bear with me. Let's run through this and let's see how it works. I think what we need to do is remember where we came from. We came from an idea of Riemann sums. Now let's recall that a Riemann sum of a function f over the interval a comma b is a sum of the following form. It looks like the summation as k equals 1 to n of f, the function, some representative point within the function. Remember, left-hand point, right-hand point within the interval, and delta x, where delta x was equal to b minus a over n. And that this sum was an approximation of the net area between the curve excuse me, between the curve y equals f of x and the x-axis between a and b. Now, that was a Riemann sum. And what we did was we chose different values, the right-hand limit, the left-hand endpoint, the right-hand endpoint. And what this did was it created a whole bunch of rectangles. So we had our curve, that was A, it came out to B, and we started making our triangles. And it was a regular partition, so they were all the same size. And we knew that each one of these had a delta x that was equal to b minus a over n, which gave you the number of little rectangles that we had. And we remembered that we had little overestimates, we had little underestimates, and different things went on. Now, if this collection of sums approached a common value, as n approaches infinity, in other words, we allow the number of partitions to increase and get greater and greater and greater, what happens then is delta x is actually getting closer and closer to 0. Okay, so if it came to a value, a common value, as n approaches 0, and what that means is the number of rectangles approaches infinity. Okay, so that's what's happening here. We got smaller and 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 smaller. Then we knew that this would become the exact value of the net area. And the way that looked was, what we did was we took the limit as n approached infinity of the summation as k approaches 1 to n of f of ck of some arbitrary point within our interval. Now remember, those intervals are getting smaller and smaller and smaller, so this arbitrary point is within an interval that's getting smaller and smaller and smaller and smaller, so that's approaching a specific point, which will be perfectly the height of that little tiny rectangle, and we're going to multiply it by its width, which is delta x, which in this case is b minus a over n, and this would equal the exact net area under the curve f of x between x equals a and b. Okay, so that's important to realize that what this is the Riemann sum, and as we allow the limit as n approaches infinity, this actually equals the net area. Okay? Now the next thing we have to remember is that we came up with a new notation for this. The new notation looked like the definite integral. It led us to the definite integral of the function f over a comma b is defined to be the limit of the Riemann sum of f over a comma b, provided the limit exists. And we came up with a new notation for that. And that notation was the summation sign over the interval a to b, the function f in terms of variable x, and this literally meant it replaced this entire set of notation. It literally means the same thing. Where delta x is equal to b minus a over n. It literally means the exact same thing, which means that this is the net area as a sum under f of x between a to b. So I have my function, it's f of x, there's a, there's b, we've put in a gazillion rectangles, all of the same width because we're allowing n to approach infinity. Let me come out here a little bit. So we're allowing n to approach infinity, so we got a gazillion nice little rectangles here. They're getting larger and larger and larger. And this whole thing here, the net area under here, a of x, in this case, is going to be equal to all of those sums as n approaches infinity. Okay, that's a definite integral. Now I'm going to stop the video here and then start it again. But my flow of thought is continuing. I just don't want to make a mistake.